Ready?
Next, we need to find the horizontal asymptote. And to do that, we must compare the degrees of the numerator and the denominators. There's three ways to find this. It's cocoa, which is where the degrees are the same, and see this one's 2 over 1, it means that it would, y would equal 2. Bobo, which is bigger on bottom, y is always going to be equal to 0. See, the degree on the bottom is bigger than the top, therefore it's 0. And then if it's bigger on the top, then it's always none. It's not even y equals 0, it's just none. And so for our case, it's 3x minus 2 over x plus 5. This would be cocoa. So 3 over 1 equals 3, y equals 3. And to graph this, you would just do a dotted line over the y value of 3.
First, you're going to start with your function. That leaves you with x minus 2, 3x plus 2 minus 2, x minus 2, x plus 5. And x minus 2 are both equal on top to bottom. So you're going to cancel them out and get your simplified right there. To find the vertical asymptote, it's what makes the function undefined. So with your x plus 5, you're going to set it to 0. So x plus 5 equals 0 minus the 5 on both sides, and that's how you're going to get x minus 5. And for the graphing, this is how you're going to graph it, as a dotted line over the x minus 5.
My name is Zach, and we are going to explain how to graph the function 3x squared minus 8x plus 4 over x squared plus 3x minus 10. So first of all, in order to do this, we must factor. And so, first of all, we're going to start off by factoring 3x minus 8x plus 4, and we're going to start by splitting that into 3x minus 2x minus 6x plus 4. And then we're going to turn those into their own factors. So 3x squared minus 2x plus minus 6x plus 4. And then we're going to simplify those and turn the simplified part, so the x and the minus 2, and we're going to make that its own factor. So that becomes x minus 2, and then 3x minus 2. That's for our first function. And we do the same for the second function. So, and that would end up being x minus 2, x plus 5. Next up, we need to find a hole, which is the point where the radical function is undefined. However, in order to find it, we must have a common factor. In our case, we have x minus 2, 3x minus 2, x minus 2, x plus 5. And we can take away these two, because of the common factor, we can take those two. And to get our x value of the whole, it's just the inverse. It's whatever makes the common factor equal to 0. In our case, it'd be equal to 2. Next, you plug in the x value of the whole, which is 2. You plug it into the rest of the problem. So 3 times 2 minus 2 equals 4, and then 2 plus 5 equals 7. You get 4 sevenths, and then you put them into an ordered pair. 2, 4 sevenths, and then you graph them, and our hole is right here.
So next, we need to find the domain, which is any value of x that makes any rational expression undefined, and that is considered a domain restriction. And this is very important, because the domain restriction, that's affected by the vertical asymptote and the x value of the whole, which our vertical asymptote is -5, and the x value of our whole is 2. And so to write the domain, we don't graph it, but we do say x such that real numbers, x is not equal to -5 and 2, because -5 is our vertical asymptote and 2 is the x value of the whole.
Find the x-intercept is when the value of x equals 0. So you're going to set the numerator to 0. So you have 3x minus 2, but you set that to 0. With this, you have a -2, so you add 2 to this side while also adding it to this side. To get 3x equals 2. To get the x by itself, you're going to divide 3 on each side, giving the ordered pair 2/3 equal to 0. And on our graph, this is here, it right here. And then, to find the y-intercept is when x equals 0. It's a substitution for 0 for x. So if 3x minus 2, you substitute the x for 0 right here. That makes this 0 minus 2, -2, 0 plus 5, because that's an x, to get -2 over 5, and you get the ordered pair 0 over 2 for this, and then this is here on the graph.
If you find everything else, you want to plot your points. So these are the points that we found out using the calculator, and this one makes a slope upwards like this. Notice how both of these get close to horizontal asymptote, but never touch. And then we have 8, 9, and 10, which is here, here, and here. And then the second line will go like this. Both of them near the horizontal asymptote, but neither one of them touching it.